Okay.
Our project is about PINN for simulation low-speed incompressible laminar flow passing a circular cylinder. And our ultimate goal is to build a PINN to solve NS equation. In order to achieve this kind of difficult goal, first we try to solve a relatively simple problem, heat equation. First of all, we consider a problem of heat distribution that has reached a steady state in a square area. We assume its boundary conditions as shown in the equations. We construct and train the PINN and get the predicted value. Our final total loss is shown at the bottom. We also calculated the analytical solution in this boundary condition and compare it with the predicted result. The analytical solution obtained by the variable separation method is shown in this figure. We choose 1,000 points for comparison and calculated the population standard deviation. This picture shows the heat distribution we finally predicted, which shows that our prediction is reasonable. So we can use this method for the follow-up more in-depth work.
After we using heat equation to prove our pins are working well, we started to work on the computational fluid dynamics. And the first work we need to do is to define our boundary condition. As we can see in the picture, we've defined our upper wall and lower wall has a velocity of 0, and the left boundary is considered to be the inlet boundary, has the parabolic horizontal speed, which will get to 0 at the corner. It can guarantee the continuity of our boundary condition. And there's in the middle, there's a circular cylinder, which also has the speed of 0 around it. And the right boundary is the outlet boundary, which has the pressure of 0. And we also define our internal loss according to the Navier-Stokes equation and choose to use 50,000 epoch to guarantee our pins are trained well. Next page, please. Firstly, we started to work on the Stokes theorem, which is linear, so it's much easier for us to dealing with. And these 3 pictures are proof that we are on the right track because they are all obey the basic physics law. And we also reduce our loss to a acceptable range. So that means we are on the right track, and we're starting to work on the Navier-Stokes equation after that. Thank you.
For Navier-Stokes equation here, we use the same boundary condition, and we only change the loss function here. So as you can see on the upper left here, we found that in the point 2, the velocity reaches maximum, and in point 1 and point 3, you can see the velocity distribution is parabolic. On the upper right here, you can see that the positive velocity and the location 1 and negative velocity and the location 2 here. On the lower left plot here, the pressure decreases along the x-axis because this computation domain here, the flow is driven by the pressure. And in the lower right plot here, you can see the pressure distribution around the circular cylinder. And you can see from plot here, the pressure increases first and then decreases. And in the middle of the x-axis here, you can see the pressure reaches its maximum value here, which means at this point here, the velocity is 0 and all its dynamic pressure transform into the static pressure. Next page, please. This plot here shows a comparison between the current pins and literature. As you can see here, our pins is able to capture the basic characteristic of the computation domain here. For example, the maximum velocity U, the positive and negative velocity V. And most important here, as you can see in the pressure distribution along the circular cylinder here, the maximum value is pretty same. It's about like 3.5. And all these results suggest that our pin has reached a good agreement with the literature. Thank you.